Okay, let's get started. My name is Sten Ingwersen, and together with Nikolaj Sovnfeldt Blom, I would like to welcome you to this mini-seminar on cold fusion, or low-energy nuclear reactions, or LENR, which is the more recent name for it. So, you probably all know bits and pieces of the historical background of cold fusion, which goes back to 1989, when Stanley Pons and Martin Fleischmann announced nuclear fusion at room temperature, something which should not be possible according to current physics. Since then, the entire field has been kind of controversial, and many scientists and organizations have been working below the radar in order to protect themselves from accusations and maybe also loss of funding. But nevertheless, LENR is live, and today we're gonna direct our radar towards it. And to this, we're very happy that we have two speakers, Bob Greenyer and Nicolas Chauvin, who are both active in the field and who are quite knowledgeable. We're going to start out with Bob, who he has a background in engineering and is coordinator, I believe, of the Martin Fleischmann Memorial Project, which is an open research collaboration in the field of LENR. And the presentation is on the new fire and other matter manipulation. Questions during the presentation, so for clarification are fine, but please, if we could leave discussions till after the presentation. Okay, Bob.
Thank you very much. So yes, I'm a volunteer for the Martin Fleischmann Memorial Project, set up in 2012 with the help of Nicolas Chauvin, who joins me here today. Can we dim the lights a bit, just a little? Is it possible? I think we didn't ask that question. So I did a presentation at Stanford in February, I think, and I think if you want to look at what's going on across the world, it's a good presentation to look at on YouTube. There's also another associated document, I think Frank Ling? Frank Ling? Yeah, of the whole sort of... Yeah, the whole sort of world of LENR. So I think those are the two documents you need to get a link, the video and the document. After this, it saved me a lot of chin wagging because I've got 50 slides and 50 minutes. Okay, so are we?
That's what I can do.
Is it? Or is it all sort of digital?
Yeah. Maybe over here.
So the new fire, that's the touchy-feely, we know what it means type name for whatever this is that's going on. And other matter manipulation. That was good, make it as dark as you like, yeah.
Okay. Don't fall asleep.
Okay, so order out of chaos. Basically, there are well over 100 theories, so if I sound confused at some time during the course of this presentation, you will too if you start to look into this. There are lawsuits at the moment. We won't go into those, but it's normal where there's a high risk and high reward in any sort of business. It's interesting that it's got to that point, that people are arguing over whether it exists in the court. Sometimes we meet our destiny on the path we take to avoid it. Well, basically, there seems to be a desire to not see this technology realized for whatever reason. And we went to South Korea in 2012 basically because of the guy that's in the lawsuit. So whatever's going on there, it doesn't matter. It got me involved again because I saw the original announcement in 1989, and I'm passionate about science and new energy. There's research going on and funded in Japan, China, Russia, India, Europe and US. I've been to several places and seen there is actually real things happening there. And there seems to be a coalescence of understanding. So sometimes I think that the theories are actually deliberately wrong. I think there's a bit of that going on. It's like, look over there, don't look here. But the truth is out there, and it only takes people to look at the history of this science to realize that it's For instance, Thomas Graham FRS in 1863 or something, he established the palladium loading ratio of hydrogen. I mean, deuterium wasn't even discovered then, but it still stands today. So, you know, this science is quite old in its foundations. Okay. So, don't throw the baby out with the bathwater. And what you're looking there is an image that I took on Friday last week. Was it Friday? I think it was Friday, Thursday. And I'll talk about it. I'm going to come back to this image, but essentially this is a piece of nickel on nickel. This is nickel. And if you see, it's like a Schallberger spiral here. And there's another one reversed on the top there. And these structures were found like on top of the nickel foil that was being made. And I'll come on to why that's significant. So this is what we're talking about, Pons and Fleischmann, the palladium deuterium experiment. This is the classic drawing from their patent. But actually, I'm not really interested in this today. I just want to tell you on this slide about this 1 cc palladium experiment. Basically, they were loading a 1 cc cube of palladium for several weeks and nothing seemed to be happening. So someone asked their kid or whatever to go into the lab and turn the power down. Anyway, when they came in the following Monday morning, there was this fine dust all the way in the air. The apparatus had basically vanished. It had gone through the formica top of the fume hood. It had gone then through and bored several inches into the ground with a hole like this. And it basically vaporized a large amount of aggregate and silicates from the floor and filled this room up with this fine sort of floating dust. It scared Pons and Fleischmann so much. So when they were hounded out of the country and told to stop doing what they're doing for whatever reason, I think it's on the basis of that, not on the basis of this little bit of technology here. Okay. Professor Francesco Piantelli, he later that year, from the announcement by Pons and Fleischmann, he was doing an experiment with a brain cell from a mouse or something, and they were looking to see what happens when a brain cell dies, because it produces chemicals to try and protect itself, but after a period of time, those chemicals stop the oxygen coming back in when the oxygen is available to the creature that's been suffocating. And he uses hydrogen to kill the cell, and then liquid helium in order to freeze the chemistry so that they can then find out what the progression of chemistry is so they can develop drugs in order to reopen that barrier so that, you know, if you're climbing up a mountain, you take a drug these days, and it probably came out of that research. Anyway, he was doing this one day, did the hydrogen, put in the liquid helium, and basically the thing started boiling. And it continued to boil and boiled, and it eventually broke the apparatus. It kept on boiling away this 250 watts of cryogenic cooling. So he was doing a biology experiment, and that then sealed the fate from 1989, August the 16th, 1989, all the way to his current days, trying to get to the bottom of this mystery. He says, I don't understand why people think of discovering anything new. Most of this research has been in the literature for the last 100 years and more. So the foundation is energy is everything. You're not getting a lot out of a chemical reaction, carbon, oxygen, 5 eV, fusion. You're getting a lot, 15 mega electron volts. Not a lot here, a lot over here. Small, big. The first aneutronic fusion was Cockcroft and Walton in 1932 at Cambridge University. And they fired a proton into 7 lithium. And you have this reaction, which is commemorated on the 2015 Irish 15 euro. And you get the lithium, and you get a bunch of energy, 17 mega electron volts in that process. So how does cold fusion, if it exists, compare? Well, you can get access to this slide later. This is from Mats Lewin. Basically, it's good on everything. I won't go into that slide. I've not got time. Conservation of energy. This is straight off Wikipedia. There's lots of people saying, oh, this is perpetual motion. Energy can neither be created or destroyed. Rather, it transforms from one form to another. For instance, chemical energy can be converted to kinetic energy, and you can read it. A consequence, the law of conservation of energy is that perpetual motion machine of the first kind cannot exist. That is to say, no system without an external energy supply can deliver an unlimited amount of energy to its surroundings. Okay, bear that in mind. We live in a sea of energy. Throughout space there is energy. Is this energy static or kinetic? If static, our hopes are in vain, but if kinetic, and this we know for certain it is, then it is a mere question of time when man will succeed in attaching their machinery to the very wheelwork of nature. Many generations may pass, but our machinery will be driven by a power obtainable at any point in the universe. Nikola Tesla. So this is the energy we might be able to tap into. Now, some people might say he was a nutter, an idiot, whatever. I don't know, but he gave his AC power and we're all using it right now. So how big is the energy all around us? Well, Steinsalk did the calculation from quantum mechanics, and he says every cubic centimeter of space, the structure of the physical vacuum, contains hidden energy of a very large amount of joules. 10 to the 20, that's a lot. This, in fact, is the primary source of nuclear energy accessible by nuclear reactions. So, this probably isn't what you're going to expect when you came here, but Steinsalk spent a couple of days with me, 4 or 5 days in Brno a couple of years ago, and he was kind enough to give me a signed copy of his book, which I encourage you to have a browse over when you finish this, signed and everything. And to my great shame, I'm sorry, Stoyan, I didn't read it until a few months ago. Oh. Anyway, you must have a look at that. He has a very different understanding of what's going on. So he says that the quantum mechanical models basically only describe energy levels. They don't describe the structure of the protons and neutrons and how they're arranged. Well, he has an idea of what that is. And they're like this. You have the protons are this kind of figure of eights. The neutrons are going around the center there, and you build up all of the elements like this. And by using this, it explains where the chemical bonds go, the ionization energies, all kinds of aspects can be derived from this without invoking all kinds of funny stuff to make it work. Okay, so you can see they're actually physically different shapes. So you can see this is short. This is spread, this is nice and grouped together. Argon's like quite compact. And bear that in mind as I show you another slide here in a sec. So, like I say, helium here, I've got both of them here on. You've got your binding energy per nucleon here. And so when we're normally talking about fusion, we're looking at hydrogen isotopes. And let's go to helium, or we're splitting the 7 lithium and getting helium. So there's an energy gain in this process. And he says it comes from the lack of distortion or greater distortion of the structure of the physical vacuum. And that's where the nuclear energy is coming from.
Maybe just a clarifying question is that what we have going on in the sun is helium fusion.
Yeah, you're getting some
hydrogen fusion to become helium.
Yeah.
And on the right we have uranium that is
This
split
is
in
sort of
fission.
happening in supernovas and coronas.
Yeah.
And this is happening in the core and takes 1 million years to get out or something.
Yeah, I'm just trying for the non-physicists audience to just clarify what the graph shows. It shows when you have, for example, in the sun, hydrogen fuses to create helium and therefore energy.
So you get a big change in binding energy, and this is the energy you gain in the nuclear sense.
And in a fission reactor, and
you're going from the uranium and you're going down a bit here, so you're gaining this bit.
Yeah.
Just to clarify, this is an energy density, so it's per element in the nuclei. So if you go from uranium, you think that there's a small amount if you go to a more stable towards Fe is iron, towards the left side, but it's multiplied by the number, by the mass of the nuclei. So multiplied by this 235. So when we go from in fusion, you go from let's say deuterium, so H2, and you have this huge energy to go to helium-4, but it's multiplied by 4 because you have 4 elements in there.
Okay, so Stoyan is saying that basically the helium here is quite compact, so you get a huge energy gain relative to the hydrogen. Did we have that on the previous one? We didn't. Anyway, because you're getting the two the 2 protons and the 2 neutrons in a really compact form. So that the bending of the space curvature, the structure of the physical vacuum is little, so you get a lot of energy gain. With lithium, you can see it's elongated with respect to helium, so it sits down here because it's distorting more of the structure of the physical vacuum. When you do a proton into here and do the Cockcroft-Walton reaction, this again ends up becoming 2 helium, and then you go from your 7 lithium here and you gain 2 of this. And he's saying that you get less energy up here from this point because what's happening with the bigger elements, and you'll see in here, the bigger elements end up getting elongated. So beyond here, the sort of nickel 62, the iron 56, these kind of areas, this is the most compact for the number of nucleons. And then this starts to slightly stretch out relative. And so for the number of nucleons compared to the distortion in the structure of the physical vacuum, that's where it's coming from. It's a very good book, this, and it's inexpensive. It will help you understand a little bit more than what I'm trying to say here. So, nuclear energy in the vacuum. The nuclear energy is released in the fusion and fission reactions as a result of sudden changes in the gravitational space microcurvature around the fused or depleted nuclei. In both cases, the energy comes from the hidden static energy of the physical vacuum. So who is Stoyanov? He's a guy that worked for the Interplanetary Space Drive Development Program under the Soviet Union, and then in 1992 he went and developed anti-gravity drives and what else? Oh, atmospheric research in Toronto, and saw out his career there. He was the plenary speaker at the Boston US Nanotechnology Conference last year, and he's doing a lot of that now. So this is the Bohr model, which we were discussing earlier. And it doesn't really help us to understand what's going on when I get to the next phase here. This is his structure of the proton and in the deuterium with the neutron here. And the electron has this normal orbit. What he's saying is that if you give it a little bit of energy, but not too much energy, you can put it into the Rydberg orbit. And in this state, it has 620 to 630 times the magnetism expressed, because the wave functions of the electron and the proton here kind of like suppress the magnetism function of the electron. And that's very, very important for how cold fusion works under his idea. So he's suggesting here to initiate this process of getting the hydrogen into the right state. At the start of the nuclear fusion process, the formation of ion-electron pairs, that's what he calls these structures, must be invoked to some external process. This is achievable by different technical methods. Some of them may be similar to heterodyne resonance mechanism, which I might say a little bit more on. But he's saying basically metal form in a powder is good, more surface area, because that allows for more ion-electron pairs. Choose the gas. You can use pulsating pressure. This is the initial approach used by Piantelli, but it's not very sufficiently effective. You're just looking at Brownian motion and trying to get it excited that way. Another method is irradiation by a beta emitting particle. A third method is irradiation by electromagnetic signal in the radio frequency range. That's why I was worried when you were talking about pointing the radar at me. Since the effective frequency depends on the gas pressure, it's more convenient to use EM pulses containing a broadband spectrum. One of the convenient ways is to use Tesla technology, because a Tesla coil can emit scalar waves, and these can penetrate further into a metal, and when they dissipate their energy, they do so at that point as an electromagnetic broadband spectrum. This is why you'll see these Tesla technologies cropping up and again in successful nanotechnologies. So, essentially, what he's saying is you end up with a thing called the ion-electron pair, and then you can resonate that. You get a bit of resonance when you do an electric strike, or you do a pulse from electromagnetic source, or from a Tesla coil, and it emits into a metal. It creates the ion-electron pair, and then it rings. So you've got the proton going between the charge areas, and then you've got the electron in this sort of, it's helix, but in a helix like two lots of helixes overlaid from one another. So you get this resonance. And this creates a big magnetic moment. It causes a coalescence of these into what some people might call, I might be wrong here, but Rydberg matter. This is, for his point of view, it's like a cluster of, it's a charge cluster, okay? Due to the magnetic interactions, the individual ion-electron pairs, they form a cluster which can move synchronously. The spatial arrangement of ion-electron pairs is illustrated here. A large number of these clusters, now if you look in the literature, I think the largest number of Rydberg atom clusters you can get, I think is 91. And you can make it out of cesium, potassium, protium, hydrogen. They're the kind of elements that are good for this. When these combine together, then you can end up these twisted superclusters. Okay? So, the point of access. The heterodyne resonant mechanism effect in properly activated neutral plasma will allow access to the zero-point energy of the physical vacuum. This heterodyne resonant mechanism permits access to the dynamic type of zero-point energy. There's two. There's the static type, that's where the large nuclear energy comes from. The dynamic is where cold fusion is coming from, according to Stoyan. It says, but it's automatically replenished by the static type. So you pull a little bit out of the dynamic type and it gets like reset by the static type. So you're effectively getting it from the static type by proxy. So what's happening is the electron, its Compton frequency or whatever he says, it's able to be using this technique, get in tune with the structure of the physical vacuum so that then you can like bleed out a bit of energy from the structure of the physical vacuum. And he's explaining the process there. Like I say, you'll get these slides, so you'll have a good idea. So he's not the only person talking about charge clusters. There's this guy, Kenneth Shoulders. And the reason I can give this presentation today is because he developed things that allowed us to make computers and smartphones. Unfortunately, he died in 2013. I never got a chance to meet him. That's very upset me, because I only found out after he died. But anyway, he has his own form of charge clusters. What are EVOs? See, an EVO is a cluster. It's a way of thinking about it, of electrons. And you know, in physics as well, you can get Cooper pairs, muons at 207 times electron, tauons at 3,477 times electron. They're all just clusters of electrons of a large size. But heck, they rarely go beyond the hundreds. And I see them into the billions worth. No trouble at all. So I'm working at a way of upscaling these class of guys. They're physically large enough that you can see them. They're about the diameter of a human hair. I've seen 5 and 20 micron ones, and my present job is to get them bigger and bigger. You've been able to see these little bitty machines make them up to 100 micrometers so far. And he has. Hey. They are stable unless I intentionally blow them up. Okay. So an electron, 511 kilo electron volts. One charge cluster with 100 billion electrons in it. Whoa, that's a lot of energy. So, he's not saying here that they need to involve the proton, okay? Or another atom that's suitable for getting into the Rydberg state. But could it be somewhere between the two that Stoyan is identified, because he doesn't really talk about how to connect. He does say you need radio frequency, but he doesn't really explain the mechanism. Stoyan's got a mechanism. So between the two, we've got a way to pull this energy out, and it builds these charge clusters. What do they look like? Well, how can they be stable? Because people are going to, it's just bonkers. They're the same charge, they'll be flying apart or whatever. You know, it can't happen. So basically, Jin worked with Shoulders. Jin replicated Shoulders' work. He said the resulting torus described by Jin and Shoulders, and they're widely published, blah, blah, blah. It basically looks like this, and they self-organize into toruses of quantum numbers, or scales rather. And it's really quite interesting, their properties. So this is Kenneth Shoulders' idea of what it was looking like. And when the National Institute of Science and Technology in the US, this is the electron accretion disks to show what it looks like. So here we got our torus. So it's not just one guy. I mean, it's like China replicated it and then they did it in America. And this guy, for someone who says this is how cold fusion works, he was funded for 33 years. I mean, he's longer than Pons and Fleischmann have been around, you know, when they were studying. It's not even that far since 1989. So, the evoid toroids generated by Scholz and Jin are self-organizing across at least 3 specific scales. There's some that you can identify. What do they look like? It just looks like a little spark discharge, right? That's all it looks like. Nothing very interesting going on there. Well, he says that this, which was demonstrated in 1904 by Tesla, this glow discharge here with the Tesla coil here, is the same thing. And so does Stoyan. They both agree that this is a charge cluster. They slightly disagree on what's going on inside it. Okay? And, Tesla's the only person that is claimed to have been able to generate, ball lightning. Okay, at will. And ball lightning, according to both of these people, and quite a few other people in the community, and all of the Russians, is a charge cluster. In fact, they have a conference at the Friendship University, one of the top 2 in Moscow, which I've actually had an opportunity to present at, every last Thursday in the month, and they call it cold nuclear transmutation and ball lightning. That's it. That's the name of this. They've had this running for 20 years. So they know what it is. Okay. Can this play?
Ball lightning, that would be in Danish, kugledyne, is that?
Yeah, it's a stable.
Yeah.
Remember what I said? That's the one thing that worried Pons and Fleischmann.
Yeah.
Can I get this to play? This is someone who's got a load of 244 dead 9-volt batteries, PP3 batteries. He's got a piece of wire, he's got another piece of wire, he's struck an arc, and then this thing comes off it. It was actually a crowd researcher that sent this video, said, "What's this? This looks like what we're talking about." I took individual frames and then made a stop motion so you can see what it's doing.
Ball lightning.
It's not burning the paper because it wouldn't. So it's bouncing. Okay, well, why doesn't it cool down? It keeps hot and then it's something that's bouncing and then it gets down to here and then it kind of gets very close to the table. Then the spark's emitted and it starts to get more energetic again. What's going on there? Now, Kenneth Scholz says these things are ubiquitous. Triboelectric effect, that's charge separation creates charge clusters. Rubbing your head on a balloon and sticking it to the wall, that's charge clusters. Getting off up a seat and going ding to your girlfriend, that's charge clusters. Yeah? They've just been calling them a different thing. Now, electrons have a charge of -1, so do muons and so do tauons, and they interact with gravity, the electromagnetic, and the weak force, like Casimir and van der Waals, things like that. So imagine that these guys have got 207 times the mass, and then you've got one that's 100 billion times the mass, and somehow you manage to get it into the Rydberg state. And already in the Rydberg state, it's expressing 320 times the magnetism. But you've got something that's 100 billion times more energy. Really? Okay. That's a lot of... Now, there's a guy called Boyd Bushman. He was a chief engineer at Lockheed Martin, and he got 2 neodymium magnets. He put them back to back, and he put a brass bolt through them. I think it was in 1984 or something. Put them in some balls, a ball of the same weight, went up 40 feet, and got some students to drop them. And there's some students down the bottom, and they recorded which ball landed first. 500 times out of 500 times, he saw the ball without the magnets land first. Well, the students recorded that. So, electrons, gravity, magnetism, and so you've got electromagnetism interacting with gravity. He proved that magnetic forces can change the influence of gravity. So, you have supergravitational field with Stoyan, and he says that everything is based off that. It's all based off magnetism, electromagnetism. So, charge clusters can negate the effect of gravity, charge, and shield inertia. Because these things are to do with the structure of the physical vacuum, and they basically negate that. It can shield radiation, penetrate ceramics. It goes right the way through ceramics. So I one of the researchers I work with, he's been studying ball lightning for 20 years, and he's taken lots and lots of photos of them just boring clean through glass or brick walls and making a nice, clean, perfect, clean hole. But he doesn't do that with metals. Okay? Transmute elements into stable products, and I'm going to go over, we just talked about Jin, the paper that he replicated shoulders. He found that very quickly he could remove the radiation, I think, of cobalt-60. No, that was Adamenko, but anyway, no, it was thorium that you get in gas lamps. He used that very, very rapidly. And Adamenko, just one strike and you get a massive reduction in emissions. Disruption of metals, and can bring about new states of material, like they glow without being hot. They turn to jelly. They're like a piece of jelly. You can put your hand in it. You wouldn't want to, because it'd be like a bit weird. Without heat, and they can turn transparent. And there's, I love citizen science. I really love citizen science. Because people say, this can't happen, this can't happen, this can't happen. Well, there's a thing where this guy called Thunderfoot, he's like a YouTuber, and he showed that if you mixed alkaline metals and you drop them into water, the explosion you get is a Coulombic explosion. Okay, and it actually ended up being published in Nature. It was all funded by citizen science. He's on a different angle right now. He doesn't know why the same mixture of sodium and potassium here that becomes a liquid, when you put it into a bottle, then it starts going black, and then it becomes transparent. This is sodium and potassium. What's going on here? And then it explodes. So what are you seeing here? This is Adamenko's work. And this is the most expensive book I've ever bought. It was £130 in digital form. It's about 700 pages, an amazing amount of data. I recommend it for some light nighttime reading. It will send you to sleep. And anyway, what he's doing, he's got an anode here and a cathode here, and he builds up a lot of charge in a near vacuum with hydrogen, and he strikes, and basically the charge clusters, according to Kenneth Shoulders, build up in here, and it goes, Pah! And you get massive amounts of transmutation. And in fact, I think I've got, here's some examples. So this was...
What is a transmutation?
A transmutation is when you take one element isotope and get another element isotope. At least that.
So you transform one state, one aluminium into silicon?
Well, so what he's got here, it says sample 20107, it's pure copper target and pure copper, the collection area is pure copper. And he's getting 21%, 22% gold here, neodymium, gold up there, 52%. These are in sample areas, but...
80% silicon.
He started from what?
99.99% pure copper in both the cases of this and this, low pressure hydrogen environment and electrons. That's it. Here's another one. I love this one, and I'll come back to why I love this one. But copper, and he's getting 71% mass in this like silver area of zinc. Here's another one, accumulating screen, again it's copper. Look at that, there's a grain down here with 74.7% gold. What's going on there? 76% gold. Wow, I want one of these. So, after 5 years, based on the data partially quoted above, at our laboratory, between 2001 and 2003, our laboratory, we succeeded in implementing and learning how to reliably produce under laboratory conditions a microscopic analog of the natural physical phenomena which accounts for the explosive nuclear synthesis resulting in the creation of a full range of stable isotopes. He nearly gets the entire periodic table of chemical elements that are seen in nature, and seems to be the energy source for supernova flares, as well as possibly a number of other astrophysical processes of the pulse nature. This process, which can be reliably reproduced, is self-sufficient in energy terms. The energy required to trigger the process is about 10 to the 4 times lower than the whole work of the process on transforming the matter, plus the total energy of the particle and radiation streams it produces. The resulting products of the process, i.e. isotopes of created chemical elements, are stable, irrespective of the activity of the target matter. Nature abhors a vacuum, and an unstable thing sitting in the structure of the physical vacuum, if it has an opportunity to be stable, it will. And what you're doing is you're making a big soup, and it just stables out. And, you know, the crystals of the friends get together and you get these lumps of material. So this means that a discovered physical process which can be controllably reproduced can be used to create efficient technologies of neutralizing the radioactive waste which would not consume much energy from energy sources. Now, of course, Kenneth Shoulders, he's quite funny because he says, like, because charge clusters neutralize inertia and they neutralize charge and mass, why don't we just like get a load of molten like plutonium, get some charge cluster gun, and because they can accelerate as if the plutonium had no mass, so in a low voltage you can accelerate up to good proportions of the speed of light, we just fire it out to the moon. Or no, not to the moon, to the sun. You just shoot the waste out into space rather than trying to remediate it. So, talking a few of these subjects, I went to India, speaking at IIT Mumbai. I gave a presentation called Red Pill, where I drew attention for the first time to the work of Kenneth Shoulders. And by the way, his site's been taken down since, where he listed all the papers, but don't worry, we got it copied everywhere. So in this case, we have a fuel mixture here in an alumina tube, an ultrasonic coupled with alumina cement to this. These are thoriated tungsten welding rods. One of these penetrates at 1.6 millimeters. This shakes, this glow discharges between here, and he claims a COP of 8. So 8 times more energy out than the power in. This is my super cool drawing. This is actually a spiral heat exchanger. It spirals down, taking up the heat from just outside the hydrogen chamber. These are the ultrasonics. There's 8 core reactors in there. Comes around through a 1-inch tube in the middle. This is where it gets superheated and comes out as steam. So, what we've got here is a foil making process. So the foil that you saw here, right? This is your Adamenko, right? So you have the round target here for your building your charge clusters. This is your flat one. And this is fluidized. There's carbon in here, which is actually quite important. So maybe I can get these to work. Oh, look at that. So what he does is it's a nickel sulfate solution being pumped down here, 2304 stainless steel bars. He's got 200 volts. It's at 300 kilohertz. All of the things that Stoyan-Sarg would say you would need to create the resonant mechanism and get this going and pulling in the energy from the vacuum. And let's see if we can get this one going. That's another view on the same shot. And it's cycling this around. It's got a plastic pump. It's got plastic pipes. And there we go. So this is his reactor. He creates this foil because he couldn't buy reliable foil from a manufacturer in India, so he's an expert in ultrasonics and plating and stuff, so, well, not plating, but surface treatment. So here's an animation of the process. So he's pulling this in and out, and depositing a few microns a second. It's a phenomenal deposit rate, but anyway. That's how he's building the foil. Now, this is something we found on the foil. Look at it, it's 10 microns long, 5 microns by 5 microns. It's like a meteorite from planet Precious. And it's almost entirely silver. Like, entirely. What's going on? This is another segment here, this little bit here, which seems to be fused in, but kind of like wasn't really there, but it's still quite large. I mean, you know, it's another 10 micron structure. And what are we looking at? Oh my, we've got gold, 31, nearly 32%. And palladium, 7%. Wow. What's going on here? So these are the elements he's starting with. Hydrogen, chromium, magnesium, iron, nickel. That's to do with the 301 stainless steel. He's got carbon from the stainless steel, nitrogen and oxygen from the water and the air, because it's just, you saw it's in air. Silicon is in the steel, and phosphorus and sulfur is in the steel, and trace elements, and argon's in the air. And everything in blue is the stuff that we see on samples of the nickel foil that's created. It's a complete surprise. This is only 2 weeks old. It's what? Didn't expect it. We went over, we're planning to test his energy technology, and we find that just making the foil component using a system that is compliant with what Stoyan Sarg would say, and who doesn't know this guy and never knew this guy, would create this environment. This is the process that he uses for processing the fuel. You've got 3 1.5 kilowatt ultrasonics horns, and they are at 19.46 kilohertz. And into here we have a sample of nickel, titanium, and carbon. And he's processing it for like 80 hours. These are the transducers doing the power delivery. Any guesses what we're getting out of this? And this is literally from test on Friday or Thursday last week. Complete surprise. He's getting loads of flat plates. What's going on? What are these flat plates? We've got titanium and nickel and carbon. What are these discs here? Oh my God. He's making lead. That's not very good, is it? Why is it? And he's making niobium. How do you say that? Niobium? Niobium. Zirconium, which is like, isn't that near niobium? You've got the zirconium there. Niobium. Yeah, lead. Let's have a look more here. And it's all the same thing that you're seeing in all those different sample points we took. Lots of sample points, because we thought, oh, something's wrong. Niobium, 3.8%, niobium, 3.4%, niobium, 3.2%, lead, like half of it, more than half of it. What's going on? But Stoyan Sarg says ultrasonics are suitable for creating this environment, because what you get in ultrasonics is you get cavitation. And cavitation, according to the way cavitation or sonofusion works, is it just causes a charge separation in which you get charge clusters formed. Done. It's the same stuff, different place. So he might have 3's a charm when we actually test the ash that hopefully he's going to send to me this week, because he might have 3 different ways to transmute matter in his lab. And I want to come back to this. Not the baby. This is Ralka, Suhas Ralka. I want to look at this structure. Now, it was a crowd researcher, a guy called Hank Mills, and I was saying, oh, it was the cathode that's round in Adamenko's work. And he says, no, it's not, it's the anode. I said, oh my God, that explains this. It explains all of these things that have crash landed, because they're not being formed on the copper substrate, the copper that's being deposited from the copper sulfate solution. They're forming on the anode and they're dropping off. And what you got here, this thing here, it's this, just on a different scale. It's exactly the same thing. And this is Hutchinson, by the way, another guy that worked with Kenneth Shoulders. Kenneth Shoulders got his samples, saw transmutations, saw the same kind of effects going on. So what connects Kenneth Shoulders, John Hutchinson, our project, and David Hudson? I won't go into him. It's Dr. Harold Puthoff, quantum physicist and founder of EarthTech International. Now, every time we had some success in our little, small, socially funded, live open science project, the company that this guy founded, who it turns out worked with Kenneth Shoulders, by the way, contacts us and says, can we help you? Go, okay, we're open to help. He has an explanation of the charge cluster stability, and you'll be able to go and see. And he explains by using Casimir calculations how you can get these structures stable. So, who is using this technology in claimed working low-energy nuclear reactions, or as I prefer to call it, new fire technology? Well, Nikola Tesla did in 1891 and 92 when he had a Tesla coil producing megahertz or very high frequencies. He had a carbon button or carborundum button in a partially evacuated globe because he was trying to create a light bulb to compete with Edison, and he couldn't have the filament. And so what was happening, the resonance in there was producing ionization or Rydberg state, and this was capturing the energy from the physical vacuum, and then it was getting electrons, and they were smashing in or charge clusters and smashing in at incredibly high velocities into the carbon. That was ejecting carbon particles. It was an atom smasher in 1891. And this was further causing resonance and charge buildup in there, and it produced 10 times more light for the same input power as the Edison light bulb in 1891. But he didn't know what deuterium was. All kinds of things hadn't been defined in 1891. Okay? But he was the first in this epoch. Bolotov, 1956, he had like dirty, oily water with a bunch of like metals like nickel and cadmium in there. And he passed it through 2 electrodes, a bit like Adamenko's electrodes. And he creates, some sort of discharge there, ball lightning. And out you get is lots of precious metals and a nice big COP, lots of extra energy. But unfortunately, he's one of these characters that didn't like to share his technology and died without really fully disclosing it. Although his patent apparently is quite good, because this guy down here looked at it and managed to do the same sort of thing and got a cop of 5. George Oshua, he took, here's an example, you take a carbon crucible, carbon electrode, 3 12-volt batteries, wire them up, and you get the Oshua chain reactions, which I will show you later. Hutchinson, 1979, Kenneth Shoulders from 1980, Adamenko, who I've just shown you, Francesco Piantelli, look at them. Electrostatic discharge leads to microwaves. Francesco's recent patent, microwaves. Norris Peary, microwaves and glow discharge. I've got a thing on that. Ernest Lakatos. This guy, he's great. You know what he gets? He gets a microwave and a waveguide, and he takes some fluorescent bulbs, and he snaps off the ballast, and he puts them in the waveguide, 3 minutes, and he gets a whole bunch of sulfur. That's 2 oxygens fusing, according to the 50s, 60s, and 70s work of Oshua, who developed the macrobiotic diet, by the way. Suhas, yeah, well, we can see what he's doing. And in fact, many of the things that Adamenko was seeing, Suhas is seeing in the same way. And Clean Planet, they're using discharges on structures designed to create heavy electrons. That's what it says in their patent, every third paragraph, without specifying what heavy electrons are. There's Leif Holmlid, and he's kind of somewhere there. He's saying that he's getting mesons out from his latest experiments, and he's ending up creating ultra-dense hydrogen. And I imagine that, if you had, and let's imagine you've got muon catalyzed fusion. The reason it works at room temperature is because the muon's 207 times more massive than the electron, and so it pulls the other deuterium atom closer to it so that it can fuse just at room temperature. Now imagine you've got atoms that have charge clusters that are replacing the electrons. Let's say that can actually happen. You're going to get really dense matter. You're going to get all kinds of fusing going on. So, this is Dr. George Eagles. We're hoping to replicate his reactor. So this is what you're seeing here is he has a microwave, a specially constructed microwave. We're going to share the plans, so you'll all be able to copy this. And he has a silicon dioxide resonator. Silicon dioxide is great because it's got the same structure as the physical vacuum in spiral form, so it can resonate itself. This produces ultrasonic frequencies. Carbon is lofted with whatever else he puts in there to transmute. And look what we're getting. This is carbon deposition around the tuned horn neck. And you're seeing these charge clusters forming and striking right there in his reactor. This is the work of George Oshua. You've got the carbon, nitrogen, and oxygen. The carbon, nitrogen makes aluminium, 2 aluminium makes iron, 2 carbon makes magnesium. This makes silicon, leads to titanium. Oh my God, these are all the sort of things we're seeing in the other work that I've just showed you, right? Okay, and this has been replicated by so many companies and so many individuals and scientists. This is something you can do at home, you know? And when you look at all these, you just need carbon, nitrogen, oxygen. And by the way, if you start with carbon and you keep adding up protons, you go round in a loop and you get these anyway. If you've only got carbon, you just need carbon. Okay, and then you get these. And then using lightning in air, you end up with, guess what? Almost every element in your body. So you just need carbon, and you end up with an environment that has everything to create life. This is his reactor. This is Dr. Alexander Parkhomov. So we're going to be, hopefully at the end of next month, running a test where we're in the EDX lab. We take the fuel, they test it on the EDX, put it in the reactor, run it for 3 minutes, pull it out, put it in the EDX. And we won't handle it. We'll just have a spherical camera recording the process. Dr. Alexander Parkhomov, he had a 40-day reactor producing a COP of, think, about 1.7, using lithium aluminium hydride and nickel. And he had these weird structures forming, like crystals of alumina. Okay? And these, do you know what this is? This is crystals of tungsten and cerium. Now, what's the melting point of tungsten? I think it's quite hot, isn't it? And this is outside the reactor, by the way. What he has is the core of the reactor, then he has a tungsten heating element. Okay, so there's tungsten there. It's not transmutation in this case. But, I mean, it's colder than the core, and the core is like 1100 degrees. So how are we getting, I mean, is it just migration? Is it Brownian motion forming these crystals? I don't know. Anyway, he's going to send us these samples. We do need a funding of about 3,000, so if anyone's got some pocket change, that would be helpful. What? If you want to help, that would be great, yeah. So we're going to do all of his latest long-run reactors, test them with SIMS. And I'm hoping secondary ion mass spectrometry. And in the case of where I'm going to test it, they're going to use gold ion, so we can see everything below gold. By time of flight, so you smash it with a high energy velocity gold atom, and then bits spray off, and then you look at how long it takes from the pulse to the target to coming off to determine what the isotope is that's coming into the detector. So you can detect all of the isotopes. And by the way, here's the thing about Adamenko. He wasn't only creating a wide range of atoms, he was creating atoms that aren't even in the periodic table. And they're stable. Like way out beyond uranium. They had to develop new techniques to be able to observe these things. Me 356, he's somewhere in Eastern Europe. He's an absolutely fantastic, intelligent guy. We hope to be testing his 10 times greater than input technology. He's got a 10 by 10 by 5 centimeter controller that is able to be, you can monitor it, you can control the reactor by Wi-Fi or online. This is because of his expertise from his other business. So he will have the best new fire controller in the business. But he actually seems to have one of the best technologies. He had one reactor running for, I think, 3.5 months between last year and this year. And he's now got a sort of commercial sort of fabricated design. These are some SEM images of his earlier technology. And he is deliberately not going to use nickel and hydrogen because there's so many patents out there, in this technology. So he went through all the transition metals which are capable of taking part in this process because of the interaction with the d subshell orbitals. So he's not using that, but he does say it's cheap. Like 6 months of power you'll get from like a few cents for the fuel load, and he's got a 7-gram fuel load. So it can't be palladium, it can't be gold, it can't be, it's going to be cheap. So I suspect it's something like titanium or manganese or whatever, chromium.
So what's he aiming at? What's his objective with this?
His objective is first to have it verified, then he's going to send it to an official verification body, then he's going to do a 3-way replication. This is what the plan is so far, and then a 100-way replication, which we have a philanthropic donor that says that they will fund that. And then from that point, the greed bug might hit, but it might not. He says that the commitment has always been that he would release the technology, but at that point, it's everywhere, so it can't be stopped. And that's the idea. So Vladimir Vysotsky in Ukraine, this is on a slightly different track and something I think that Steen's going to have another seminar on at another time. And this is, he took cesium-137, which has a half-life of 30.17 years. He mixes it with what he calls a syntrophic colony of brewer's yeast and methogenic sea ooze, which is bacteria. from seabed because it's then salt resilient. And he shows that after giving it some nutrients, after 2 weeks, he changes the radioactive decay from 30.17 years to 270 days. This is some of the sludge at the end. He has replicated it once in the sarcophagus in Chernobyl and twice in Russia. He wants to do it in Europe, and we have a funding requirement for that of 150,000. Our major challenge is to get a single isotope of cesium-137. Good luck with that. Okay, Norris Piri. Now this is why I said about pointing the radar at me earlier, because radar's a microwave and microwaves would take down anything that used this kind of technology as a power source. Because he takes a palladium rod, he loads it electrolytically, a bit like Pons and Fleischmann. And he was doing like what Brillouin were doing. They were using a pulse, and he was getting it faster and faster and sharper and so on. But they just reached a technical limit, however many years ago it was. And the guy said, I can't go any faster, but I can get a magnetron. Okay, let's get a magnetron. And so he has a glow discharge. He has this wire in basically a vacuum. So there's palladium, deuterium in an alumina vacuated tube, and a glow discharge through 2 electrodes and a microwave. 20 microseconds on, 100 microseconds off. If he goes any further than that, then the whole thing melts down. The alumina vaporizes. And guess what? He gets every single element in the periodic table very quickly, like a capacitor discharge. Now, he knows what he's got, and he's asking for 1 million for 1%, and he wants 15% to make it commercial. So if anyone wants someone that's purely on the commercial route, but he's been working for 26 years in an island. It takes a certain quality of person to be able to do this. This is Francesco Celani. I put him in here because he enabled our project, because he let us use his technology. And that started the project because some scientist was brave enough. And on our third test, we saw 12.5% excess, and you saw 10%, I think, in your...
Yeah, around 15.
Okay.
20 even.
Okay.
That's stable, so between 10 and 20.
Yeah. He's got much better wires now, and he's actually working off the insight from Homlid. He agrees for us to openly record the entire working process to create the wires, the active wires, but there's a funding requirement for that. So what can the new fire do? It can create heat, light, and electricity. It can neutralize radioactive elements, and it can synthesize elements. So I'd like to thank all these people, Francesco Celani, the incredible crowd, which has enabled our project to accelerate at such pace. I mean, think about it right now. We have 3 of the leading technologies and 2 of the technologies that have done long runs with Reactor. In fact, 3. Parkhomov, Me356, and Suhas. They've all had reactors. Suhas reactor's been running like 9 months off and on, but for about 3 months in total time. But the crowd have really enabled it. I mean, they've given us money to do the tests over the next 2 months. We'd especially like to thank these donors, New Energy Foundation, Bobcat Sverige, Sweden, Hunt Utility Groups and Magic Sound, some people that loaned us equipment, some universities and institutions that helped test University of Missouri and Aarhus University, and Earth Tech International, thank you very much, Harold, and the very many private donors. So, with that, if there's any time left in the day, I will take questions. I overran by 15 minutes, sorry.
Thank you very much, Bob, for a presentation with lots of information and lots of controversies.
Yeah.
Controversial stuff. So, I would assume there would be some questions here.
Yeah, you haven't mentioned Andrea Rossi.
I did. I said there's a lawsuit going on. And I said the person that's involved with that lawsuit meant that both Nicholas and I got involved with the project.
Okay, right.
So I know someone who's exactly the same character as Rossi. He's a full-time inventor. And so nothing that he does surprises me at all. and the protectionism and all of the shenanigans surrounding that, whatever that may be. You know, I like open science. I like things I can touch. I like when I was with Suhas, he says, here's a sample. In fact, I've got them here. You can have a look at them. He says, this is a sample, this is a sample. In fact, he just gave them to me. There's the foil. You can pass it around amongst yourself. Don't touch it. That's what I've got left after doing analysis. And he just said there, and he just thought it was going to be nickel foil. Didn't know it was going to be all the precious elements on there. Copper as well and things.
So maybe some more background. If some of you don't know about Rossi, could you very briefly explain what he has done?
He looked whilst he was having some free time at his government's pleasure at a wide range of research in the field, which is what I was saying to you right on that early slide. The truth is there, it's already published, and a lot of it is very old. It's what Piantelli says. Just people are ignoring it because every time you raise the subject, someone says, oh, that doesn't exist. It doesn't exist. Don't look there, look over there. Don't look there, look over there. And so the problem is if you spend 2 or 3 years, you end up getting excess heat, and it's like, okay, now I have to convince the other people that will say it's rubbish. And then you get locked in this cycle.
So he claims to have 1 megawatt.
Well, he claims to have a guaranteed output of 6 from input. Now, if you look at Bolotov, he was claiming 7 or 8 or 9 whenever it was in 1956. You know, these things are not great claims to make. You know, you've got the same, much bigger gains claimed by Adamenko. You've got bigger claims, in fact, claimed by Suhas and Me356. You've got vastly bigger claims by Piri. You know, these are not large numbers, and it's not surprising because you've literally got infinite energy out there. The trick is to not destroy your reactants. It's a balance. It's a yin and yang. You mustn't take too much, otherwise it's game over. It's like, take a bit, give a bit, take a bit, give it out. So
what's the danger?
The danger is that if you, like, so for instance, Piri, if he goes to 21 microseconds, his reactor melts down. So it melts down, and as I said to you before, it's basically no radioactive. The radioactive elements you get are tritium. And this is what they were looking for. Of course, charge clusters can shield radiation according to Ken Shoulders. So this is the explanation for why you don't, according to him, anyway.
Okay. Anas?
You didn't mention Randall Mills.
Because he says it's not cold fusion. My own view on that was expressed, and then I was asked by his company to remove the video. But anyway, I believe it's the same family of technology. It's bringing in energy from the vacuum. He has a nice, interesting thing to explain it all. Complicated enough so that most people won't look. I mean, most people won't look at any of the simple stuff that explaining cold fusion. They're certainly not going to look at that. But there are people that have seen it. They've said that at least this formula explains what he's seeing and the observations, but then so does normal science explain nuclear energy. So, you know, you can make an explanation that fits, but is it the right explanation? I don't know. He might have it, but his explanation doesn't seem to explain all of the other things you observe across the whole spectrum of this science. And I think Kenneth Shoulders and charge clusters and somewhere between that certainly explains all of the high power systems that we're seeing now. It's a very elegant system, but yet he's yet to be able to put the lid on, as I understand it, for any length of time. So he's got a lot of technical challenges still. So I wish him well, because the world needs competition. That's great. But, you know, Suhas has got a technology, Me356 has got a technology, Piri, if someone's wanting to go there, that he's got a technology, so there's a selection.
Could you maybe spend a few minutes on explaining about the Martin Fleischmann Memorial Project?
Why not?
How many are you, and what are you doing? How are you working together?
So basically, we are a group spread out over the world. Some people are dark at the moment; they're going to come into the light. But those, when they're in the light, they're basically running experiments. So you've got people like Bob Higgins. He's running an experiment last weekend. And we run our experiments live online, and we say, this is what we're going to do, this is our protocol, this is the equipment we intend to buy, have you got any better ideas? This is how we intend to fit it together, have you got any better ideas? This is the protocol for the experiment, have you got any better ideas? And then here's the live data, can you have a look at it whilst it's being fed to you? And the amazing thing is we have sometimes, 100-200 people looking at the data, and we get graphs back, we get suggestions back. When we've got a problem with, trying to explain something, we'll put a question out there. And it's like having a lab with 1,000 people in it, or 2,000 or 3,000 people. And they all really want to help. It's absolutely wonderful. So,
and each get their own funding, or how is it?
So essentially, people like to support the projects that they can identify with and they can see maybe has a chance of moving somewhere. So periodically, if some claimant out there has something that looks really interesting, we will go out to the crowd and say, look, this is what they're claiming. This is what we would need to be able to test it. And if we get the support, then we can go ahead and test it. Other than that, then if we've got a little bit of spare cash, which is not a lot, we do our own experiments. But we're not so much about creating the technology. We're about seeing which theory is actually right and or helps guide the research, and educating the best education we can to guide people who might be interested, and then to verify technologies. But if the claimant has a patent, we don't mind. I mean, Chelani's got a patent on his wire production process, but he's openly sharing the technology, and we wish more people would do that. I wish Peary would do it. He's got a patent pending. Let us test his technology. I mean, it's an open and shut case if his claims are correct. It certainly looks like it's correct because he's doing everything right according to whatever seems to be the way to get high energy here. So, yeah, there's a range of ways that we interact. And then we have a lot of people from NASA or Department of Energy or universities. When we have some interesting thing, they'll say, can you send us your data? And they analyze it and they send it back and say, you got nothing. Normally. But that's helpful as well. And that's the point about being open. We make the mistakes that we make, or the errors in the data, or the errors in the assumption are found like that. And you don't waste months and months and months wondering whether you're going in the right direction. Sometimes they'll tell you something wrong and you find that out because you have this curating process by the crowd. So you'll say that someone said this, and then like 10 people will go, no, actually that's wrong. It's absolutely wonderful, really, as a process. But it wouldn't work with everything. There's an emotive connection to this. When this technology is out there for everyone to use, in a generation they'll just be saying that this is what energy I get for my money. They won't see it as. I call it free energy because if I give $1 now and I get $1 worth of energy, and I might get $1.01 from this guy and 99 cents from this, but if I give it to Suhas Ralka and I get $8 back of energy, I'm saying I'm getting $7 of free energy to me. But in a generation, they'll say I'm just buying $8 worth of energy. So it's a beautiful transition. The other thing is about elements. When you understand that just with carbon, there's an opportunity with charge clusters to create every element for life. You don't need a planet that has water. Well, yes, you do, actually. Water and carbon. And then you've got everything.
Yeah.
Anything else? Anything?
No more questions out there?
Okay.
Actually, I have one more.
You can have as many as you like.
So you mentioned really, there's a lot of stuff there in your presentation. You mentioned a lot of people. So can you briefly sort of give us an impression, how far are we from sort of real applications, so industrial applications, or is that possible to say by now?
So the typical research in this field that gets far is working with extreme levels of expertise and passion. And what they typically do is sink all of their own funds into it. And they get to a point where they know they're there, they know that they're there, and they have no idea how to go to the next level. They literally have no idea. And what typically happens is someone that knows nothing comes in and tells them not to do anything. We don't want to know. We'll buy your technology, but then we're going to put it under there. So, or the greed motive gets in. And greed is the biggest killer of this technology since the beginning of the last century. Every time they get so far, they want a big prize for it. And, you know, if they get the big prize, it's shut up. If they don't get the big prize, they still want the big prize, and then they die. So part of the process of the MFMP is to try and encourage claimants to be open about what they have and to have that documented and documented in an accessible way. As I was saying to you earlier, you know, people read the abstract, the conclusion, and maybe one graph that looks interesting in a paper. That's 99 times. I don't know. Maybe that's just me, but but a lot of the meat is lost because people can't identify. They can't feel what's going on, and so I think science needs to do what's happening on YouTube with like that guy Thunderfoot. He's got like, I don't know, 1 million subscribers, and when he does an experiment, there's a lot of people paying attention. So if you have an experiment and you want to get exposure, get him involved. You know, don't get us involved. We've only got about 1,800 or something. But yeah, so it's been the most interesting thing I could possibly have done in the last 4.5 years. It's made me poor, but it's made me mentally very rich. And I can't imagine meeting more interesting people, really. And I'm sure in this room, there are some phenomenal minds. And I wish I had time to spend a day with every one of you. Anyway, thank you for listening.